Let's should we get started kind of semi on time, or should we wait for people? What do you think? It's a good idea. I like that kind of thinking here. All right. Awesome. We've shared the screen. Everyone's ready to go. Pi reports on Twitch that he forgot to come to class today. That's okay. Yes, he's here digitally anyways. All right. So it is now week 11 by my reckoning, because I just graded the week 10 write-ups for the CTF extra credit. So things are moving along. Let's go through the meme review, the current status, and then I want to talk today about how symbols are resolved in binaries, right? How library functions are found in memory, and then how you can find other library functions given the address of one library function. All right. So starting our meme reviews with some frustration, it's, oh, God damn it. All right. So starting off the meme reviews, weekly reminder that hexadecimal is not decimal. It's not just cursed decimal. It's actually its own base with different implications. So yeah, be very careful. These sort of mistakes can just lead to enormous amounts of lost time and headache. And as always, if you feel you're really stuck and you're stuck on something that should not be this difficult, there's always the help channels as well. Of course, that doesn't always help. You might still get pretty bad news. All right. Awesome. Let's move on from there. The different exploitation techniques. Different people have different ways of approaching exploitation. I really appreciate this meme on the left of the slide here. It's good stuff. We're going from knob sleds to red sleds, and maybe one day you'll be ropping through Yan 85. Who knows? That would be pretty cool. All right. Another thing, just because your exploit doesn't work every time doesn't make it a bad exploit, right? The kind of, I mean, every situation is different, but oftentimes you can fire an exploit multiple times, especially to prove that something is vulnerable, right? If you're doing creating an exploit to show the exploitability of a bug for a bug bounty, if your exploit is super unreliable, it still counts as the proving of that vulnerability. So in some of these challenges, you will need to brute force a couple of nibbles here and there, but you can do it. Actually, you know what we should do? We should add a brute force thing into Embryo.io, just to get people to brute force something in the very beginning. Can you write that down? That would be awesome. All right. Awesome. Okay. Yeah, so it's pretty good stuff. Don't be afraid of a little bit of brutality in the brute force. This is great. I love these memes. And I'm just bummed. I think 766 should probably be 755, right? Is my guess, is what was intended. But other than that, awesome meme. Nothing to do with what we're doing right now, but good stuff. General Linux meme over here. Interesting thing. I think we've discussed this earlier. Root can still read files that are 0, 0, 0. Why can root do this? Root can do this because dash dash list dash dash prints. Every time I have to relearn this. All right, root can do this because it has this one. That I think this is data access control override capability on, or at least, wait, why do I have it? No, I don't have it. Okay. Good. My current capabilities are blank, but if I become root, equals EP. This is what happens when I go off script. Anyways, this capability, capdac override, allows root to read files that are otherwise not accessible. And you can actually grant this capability to a user process using the set cap command, and read 000 files. It's very fun. Anyways, it doesn't really matter in normal practice, but here you are. All right, this is a lie. I don't believe this was you. It's not a lie. Huh. So Raman claims it is not a lie. I that's impressive. I think without heavily using GDB, it'll be very, very hard to get this far in the course and stay at the near the top of the scoreboard, and with a reasonable grade. That's impressive. GDB is GDB civilization. GDB is why all of you got into computer science. You just don't know it. Didn't know it until now. GDB is, to put it lightly, your destiny. Anyways, don't forget to use GDB. This has been your weekly reminder. You didn't have a loophole where you were using a different debugger, did you? Just Ghidra in your brain. Pretty good. You have an emulator inside your head, that works too. All right. Awesome. We had a student from last year drop in and give us this awesome meme about Jan 86, as they said, but it's actually Jan 85. But that's okay. It's the thought that counts. And then this is great. We had the camera malfunction and the belting ceremony. For those hoping to get a belt today, I'm sorry I went straight here from home instead of going to the lab first, and I didn't bring any belts. That's my bad. I didn't realize it until like just now. But next time we will have belts. But my daughter went back to daycare, so probably I'll be sick in like a couple of days. All right. And then of course there is some suffering in the class, but it's all character building. This is all very, very important stuff. All right. Memes out of the way. Let's see the state of the class. Basically, we saw Anubis defend their top position. Well, I'm assuming you pronounce this Anubis. Otherwise, it's Anubis. Defend their top position by racing through Baby Rob. We have also very interesting. Trees and Ramen are and then Nighthawk are the top 3, 1, 2, and 3 ASU students in that order. And then Naughty Boy also managed to remain in, and Haka Roots jumped up in the top 5. So great job. This is good stuff. The video meme. Oh shit, I forgot to put the video meme in there. God damn it. All right, I'll try to get the video meme. I mean, we have next time as well, so don't worry. Don't worry. All right, anyways, great job. It's insane to see again the amount of yellow belts. I think this is more yellow belts than we had like by the end of the class last year. So this is pretty crazy. Hopefully this means our material is more smooth. And yeah, awesome stuff. Keep pushing onwards. All right. One thing that I wanted to say about this scoreboard. Oh yeah, also awesome to see the amount of worldwide students that are here. That's crazy, considering that you all have to stick with the challenges and lose all the sleep. These people are just doing it to themselves out of some insanity. But very cool. You guys are doing great too. All right, how are we doing in CTF extra credit? Fudge, I did not update that. Can't be perfect. All right, last weekend I did update those stats. 10 students on 3 teams solved 10 challenges, 10 unique challenges on Buckeye CTF between them. So one team solved 8, another team solved 6, another team solved 2, and out of those there were 10 unique ones. So great job. That's 8 challenges for a team that's been playing for 10 weeks. Super impressive. There's still 6% extra credit available. That's 1% per week for the remaining 6 weeks. So think about that if you're concerned about your grade. Let's check what CTFs are happening this weekend so you can start planning. This weekend we have, besides Jeddah, that seems to be the most popular. Oh, Haklu. Haklu is awesome. I've played quite a lot of iterations of Haklu. And then Killer Queen and Kettle and Piratica Risen. I'm not sure which ones of these will be on the easier side, which one's on the harder side. Haklu, I would imagine, will be fairly difficult. It's a very long-running CTF, but check it out and go from there. Awesome. All right. So go play some CTFs, submit your write-ups, and get your extra credit. Actually, one interesting thing from this CTF, there was a challenge called Buttons, and it was a Java application that I think you were supposed to like decompile and figure out how it works and figure out how to press the buttons the right order. There was a student that just brute forced the challenge and figured it out. Is it someone here? Amazing. I was reading it, I couldn't believe it. I mean, that was awesome. That must have taken a lot of very careful tracking in your mind. A great pattern spotting. That's insane. That flag must have been really confusing when it started talking about Java, because it's that's great. Awesome. All right. So yeah, more CTF available, and 1% per weekend. Okay, helpfulness. Derek maintains supremacy, but there's a bitter battle ongoing for the top slots. The reason I wanted to bring up this slide again is please link your Discord to your pwn.college so that we can do the extra credit properly, right? So go into dojo.pwn.college, go into settings, there's a Discord section, link your Discord. That will enable us to eventually pull this information in. That's only if you want to get the extra credit. Otherwise, the extra credit of the reputation of your account will be evenly distributed to everyone else. But obviously, that's less good for you. All right. Let's see what's going on Twitch. Oh, Killer Queen and Kettle CTF say that they are high school level CTFs. That might be good to tackle. Kettle is natively in Russian, so I don't know if you want to learn Russian, or if you know Russian, you can tackle that. But yeah, it's tricky. It's tricky to try to play CTFs that aren't in a language you can understand, because even if you can understand the problems, you often miss hints and other things. So yeah, that's tricky. All right, I once played actually. What was it? I think it was either an iteration of CodeGate or Secu Inside, or maybe some other CTF out of Korea, where everything was like in Korean and then Google translated into English, and I actually missed a problem because they mistranslated some encryption term, and yeah, it was no good. All right, anyways, let's roll on from there. So where are we in the schedule? We are in the second class of return-oriented programming. Will there be a third class? Probably not. Right now, people are on actually a really good trajectory, comparatively speaking. So we will have to, I'll reevaluate tomorrow, but I think we might be able to continue on time, which will be great, and give everyone a bit of a rest day for Veterans Day. Let's take a look at grade-wise. You can see many grades are on the uptick from Toddler 1, not all of them. I think people that are tackling these problems, of course, Baby Rop, Toddler 1 is kind of like the midterm in some sense, and Baby Rop is back to the more normal, like exploring of single concepts. So don't sleep on these challenges, go do them. Don't count on that extension. All right. In terms of distribution of grades, of course, it's still early, so we have very few people that are all the way through and so forth. It's looking like this, which is actually much better than most of the other challenges have been 2 days before the deadline. Basically, the top 25th percentile already is kind of approaching, kind of passing, but this is what things are looking like for the actual grade distributions. So go do Baby Rop, then and let's make it happen. All right. If we ended class today, our uncurved grades looked like a good bell curve, except for this huge amount of people that are failing. Of course, I think about 20 of them are kind of delayed withdrawals. With the curved grades, we still have a pretty good bell curve, and around that B, with, if we assume that many of the E's are withdrawals, things are looking fairly okay for now. So we're not going to change curves in the middle of a module, but for now we're keeping the curve stable anyways. All right, the I grades. Based on some feedback, I added a status check. So if you didn't hear last time, I'm going to offer an I grade option for those people that had, as ASU says, those people that are doing acceptable work but are unable to complete the course because of illness or other conditions beyond their control. So if this applies to you and you can complete 1/3 of every module and you want an I grade, that means you will finish the course later and I'll update your grade later. The later is a deadline of August 1st with a status check to make sure you're halfway there, halfway through the summer, 1.5 months after spring semester ends. The completion, the definition of completion is much more strict than during the normal semester. So you could potentially be at a spot where you have like a B in the course, you take an I grade, and then that B, if you do nothing by August, will translate into an E. But if you need that time, that's 8 months of time that you can use to catch up from unexpected illness or other situations. All right, if you have feedback on this, it's not final policy yet, but we'll make it final before the drop deadline so people can make informed decisions. Just let me know. Otherwise, baby ROP is due on Thursday, and then we will move on to the heap, and that'll be super fun. Any questions on any of that? No questions? Here? Not on Twitch? Awesome. All right. So today, we are going to talk about library function resolution and its implication on ROP, right? As you've noticed from the challenge problems, you very rarely actually make syscalls. In shellcode, you made a lot of syscalls. But in ROP, the syscall gadget is fairly rare, right? If you do RP++ on our little binary from, there's Ropable. Yeah, so here's Ropable.c from yesterday. We do RP++ on Ropable. And we grab for syscall. No luck, right? The OF05, is that right? For syscall, I think. Anyways, that byte combination is just rare for whatever reason. And also for security reasons, some security conscious compilers actually try to explicitly avoid it, specifically because of ROP. If you process something that uses libc, of course, it'll have it. Let's grab that. First, that uses syscalls, such as libc. It'll have it. There it is. Syscall gadgets galore. If we even search for int 80, of course, that exists in libc as well. Does it? No, int 80 does not, which makes sense because it, oh, yep, it does. Couple int 80s. So basically, libc has syscalls because it does syscall. So somewhere in there is code that does a syscall. libc also has syscalls just randomly because it's big enough, potentially, depending on how it's compiled. So randomly at some point, part of another instruction is going to be 0f, 0.5. But these small challenge binaries you're facing oftentimes won't have syscalls. So what do? How do you actually cause actions to be taken on the environment? Well, last class, we were jumping to what I casually mentioned was PLT stubs in the binary. And in the fundamental lectures, I mentioned this is how symbols get resolved. Don't worry about it too much. Now we have to worry about it to at least some extent, right? So let's take a look at Roppable under the microscope here. All right. It's a very simple program. All it does is do a read to overflow the buffer, and then it returns, and then all hell breaks loose. If you, in IDA, double click on this read, IDA is not going to open libc, even though read is a libc function, right? And let's actually double check in our awesome GDB. If I break on read, I continue, boom, I am here at the breakpoint in read inside libc. This looks like a libc address, and you can so FFFFD880, and oh no, that's the buffer. Sorry, where am I? FFFF, there, that looks like a libc address, 7EC blah blah blah. That's going to be somewhere 7E, somewhere between here and here in this inside libc. All right, so we broke in read, we ran, we ended up in libc. How did we get here? Right? How we got here is a tale fraught with subtleties of history, and could probably stand to have a couple of lectures of its own of measures and countermeasures and countermeasures. But basically, here's how we got here. Here's the read function. When we call the read function, where do we go? Let's start over again. Okay. We're gonna step until main calls read. And what we see is it calls read at PLT. This call is a call into a binary, an address within our binary. It's a call into a function in this binary, not in libc. And boom, now we are in the binary. We're in a function called read at PLT, or that's what GDB calls it. IDA calls it underscore read. What it is a PLT stub for read. So what does it do? It does this insane thing. It does a jump. I don't like how IDA shows this instruction. Yeah, this is a little better. It resolves some rip relative offset, loads this address, and jumps there, right? So it'll jump to, it won't jump to rip plus 2F95. For that, you wouldn't have these brackets. It'll read the address to jump from there. That address right now is 404.015. More in direction, right? What the hell is going on here? So we jump in, we read some crazy address from somewhere, and we're gonna jump there. And then I will tell you what that crazy address is and what the place we read it from is. Boom. All right, now we're in question mark. So GDB has no idea where the hell we are. We're still in our binary, but now we are pushing 1 and jumping elsewhere in the binary, right? So now we're jumping somewhere in the binary with 1 pushed onto our stack. Boom. Now where are we? Somewhere else in the binary where we are doing some other stuff and jumping to an address stored even elsewhere in the binary. And then that address that's stored in our binary finally takes us into some crazy code in the library LD. What is this library? We haven't interacted with it heavily yet, but I talk about it in the loading of ELFs lecture. We can actually, it's the Linux, or it's the dynamic loader in Linux, and we can actually run it, and it'll just tell us, hey, you've invoked LD, and blah, 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 blah. What it's telling us is basically LD is a library that handles the loading of libraries and the resolution of symbols in those libraries. And what we have just gone through, that big long process of jumping all over the freaking binary, was a process that ends up with us executing this resolver code in LD that finds read, resolves it, and returns there. How do we know that it's read that's being found? This function in LD, this isn't the resolve read function, it's just the DL resolve function. Anyone want to guess how we know it's read? We know it's read because of this push 1. So Detroit Demon on Twitch, oops, I highlighted the wrong line, this push 1. Detroit Demon on Twitch speculated maybe this is the syscall number. This isn't the syscall number, this is an index into the binary that my mind went blank. In the binary, there's a strings table that is indexed by this number, and index 1 of that strings table is read. Index 2, or of that, that strings table. Index 2 is going to be, what else do we use in Roppable.c? Yeah, let's look at exit. And here we can pick up either underscore exit, does a jump, blah, blah, blah. It's going to be going to here. Nope, this isn't the X string. What's the easiest way to look at this code? It's going to be near the libc code. Yeah, in fact, you can even see it in the preview of the next few instructions. So we go to 401044. So this is the libc, or the read resolver stub. All right. If we look at here, control, I don't have a numpad. God damn it. I hate this about IDA. I rarely enough expand these guys that, here we go, on hide. So this resolves read. This one, we see where it is let's actually do this. Hold on. Let's break. Let's break at so here's the win function. Win, if you recall, just calls exit after we messed with it enough last time. Let's put a breakpoint at this call to exit, and we'll walk through what happens when you call exit, and we'll see that it pushes a different number. And it's probably going to be number 3. So if we do this, we set the rip, let's just YOLO this. Could have also just overflown the stack of this buffer. Continue. All right, we are about to call exit. We step. All right, looks familiar, right? We're in exits PLT stub. We're going to read a value from later in the binary. Okay, and we're going to jump there. Boom. We're in a resolver stuff that looks very similar to the read one, but instead it pushes a 3. All right, so we pushed 1 to find read, pushed 3 to find exit. Why 1? Elsewhere in the binary. Here it is. Except for this doesn't agree with us. Here's read. Oh, okay. So here is read, puts, and exit. The actual strings, you'll see they're not in the order that we expect them to be. We expected read to be before exit, read in whatever index 1, exit in index 3. If you look at where they're actually referenced, this, okay, also unexpected. Neither of these orderings match what we expect to see. Does everyone agree? Expect read to be in index 1, exit to be in index 3. This is, okay. This is closer, but this is different. This is a jumper location table. Okay, so here, okay, yeah, that's the global offset table. Let's do this for libc start main and see what the index is. All right, we're in start and we're in okay. Let's break and start. Okay, we're in start in the binary. Set everything up. And then we call and libc start main is already resolved. Because it uses relocations. All right, well, let's just agree that there's a bit of a mystery here. The point is that index indexes into ELF structures that ends up telling the loader, hey, we're trying to find read. Hey, we're trying to find exit, right? How it as actually, found inside the ELF headers isn't as important. What's important is that it only does it once. Let me show you what happens if we have a function that calls read twice. And let's okay. Actually, let's do a start. Okay. All right. Fuck, it's dash p, no bind, not dash dash, no bind. Okay. All right, we're in main. This function is going to call read and then call read again. We're going to go walk through it. Here we are in main, setting everything up, blah, blah, blah. Calling read. Boom. We're in the PLT stub of read. Boom. We're about to jump to some crazy address stored in the binary. Here we are at the resolve stub for read. We're pushing 0, not 1. Those indexes depend on also what else is in the binary, right? So in this binary, read is index 0. Okay. We jump to the part in the binary that sets stuff up and jumps to LD. All right, let's just get out from, actually, let's walk all the way through here. So this is LD executing code that is looking, parsing ELF structures, et cetera, et cetera, et cetera, looking for read in libc. I just want to not miss. Let's just keep stepping until we get to it. So we're stepping. A lot of code. It's gonna might be a while actually. We're doing a lot of stuff, right? To find where read is. Come on, how hard can ELF parsing be? Aha! Shit. We ran all the way through. Okay. So we were in LD, and then somewhere along the line, figured out where read was, set it to register R11, and somehow suddenly we're executing read because it jumps there, right? How cool is that? The resolver crawled through ELF header structures, found where read was, now we're executing read. Now, suddenly we're executing exit. What the hell happened here? I will show you. Let's start again. All right, this time we'll step through it. Actually here, we step into read again. We jump somewhere to some address that's stored somewhere in the binary. We'll talk about this very shortly. Boom, we're in the resolve stub. All right, boom, we're in some more generic resolver stub in our binary. Boom, we're in LD resolving read. After this, finish. And we're waiting. We called read, right? Let's give it some input. All right. Wait, what? Where's my second read? What the fudge? Did I forget to call read twice? Oops, I screwed this up, guys. Sorry. Doesn't matter. Everything we did so far is still okay. But now we're calling read twice. All right. Here we go. We call read. We call read. What the hell? Where are we? Yeah, never mind. Here it is. We call read, and then we call read. All right. Let's step through it again. Boom. We jump into that indirect offset. Push 0, signifying read onto the stack. Jump to the generic resolver, jump into LD. If we go keep running, we find and execute read. We give it input. All right, great. Now we're calling read again. All right. So we jump to the read PLT stub. No problem. Makes sense, right? And we're about to get the address that's stored somewhere else in the binary and jump there. Previously, that led to the read resolve stub, which would push 0 or whatever ID read had in the ELF and go on from there. But now, boom, it takes us straight to read. All right, why does it do that? Well, what's the point of re-resolving read? We know where read is now. Let's just keep using that address, right? And of course, we are reading again. So what is that place where the address of read is stored called? It's called the global offset table. It is a table maintained in every dynamically linked object, such as this binary or even libc or even other libraries that link against anything, and it is used to store the resolved address of whatever you're trying to resolve, in this case read. And if we look at what happens before and after on this read binary, if we look at what is here right now, this is that resolver stub, reads resolver stub, right? And if we step all the way through it, the next time we execute read, or really after that first time, after DL resolve ran, it updated that location in the binary to point to the actual read function. Cool. Ethan's amped up. He looks asleep. Awesome. All right. So this is dynamic symbol resolving. How it worked. I mean, obviously it still works this way, but this used to be a hell of a lot more relevant because these global offset table things were very common overwrite targets. If we overwrite this with system in some crazy way, then the next time that we call read, we'll call system. The arguments don't line up, but you get the idea. You can redirect control flow potentially arbitrarily. Nowadays, things are a little harder because of something called RELRO. Let me Okay, here we go. Oh, interesting. Yeah. So apologies to anyone on Twitch. My Zoom is telling me that my network connection is unstable. So probably this is impacting Twitch as well. There's an emerging technique of defending against overwrites of the global offset table. And this technique involves resolving everything at program launch time and then remapping the global offset table read-only, right? It's a great technique. The problem is, in order for it to be truly, truly effective, it has to be applied to all of the GOTs of all of the binaries on the system. Or rather, all of the GOTs of all the libraries that are loaded when your vulnerable process runs. That's not always the case. It's not something that you necessarily have to worry about right now, but because of the popularity of these mitigations, we actually don't look at GOT hijacking in that classical sense in this course. But where the GOT is useful is for leaking out the addresses that are stored in it. As you saw, in GDB, where's my GDB? When we first start up, the GOT entry of read, and again, the GOT is basically just a bunch of, this is the GOT of different binary, but it's just a bunch of addresses of these library functions that start up depending on what's enabled in terms of mitigations and how it's launched as addresses into the binary. But after you call read the first time, it's a libc address. But if the main binary doesn't have PIE enabled, you know this address. You know where the libc address is stored. Why is this relevant? Because this can be used to leak out the address of libc. And why is that relevant? It's relevant because the moment you have the address of libc, and if you have the libc itself, then you can determine the address of everything else in libc. The moment you have a libc address that you can nail down to, hey, this is the address of read, right? Then obviously you can say, okay, I know that read is cc130 into libc, into the file. So that file must be mapped at 7E0000, and thus you can calculate the address of every other function, every gadget in libc. Now, what if you don't have the libc? This isn't a problem for this class. You have the libc, it's the libc we're using here. But if you don't have the libc, maybe you should make it a problem for the class. What do you think? It's a good idea. Anyways, let's write it down. Not for this year, obviously. If you don't have the libc, but you can leak out several addresses. Let's cheat and here's read, and here is puts. All right. There are libc offset databases on the internet. Wow, my laptop is barely keeping up with streaming. And I usually just try random ones until I find one that works. And you can put in an offset. Here is libc read, and it's going to be at offset 130. And here is puts, and it's going to be at offset 5A0. Let's find the libc, and it tells you you're fucked. It didn't work. but maybe a different libc will fare better. A different libc searcher. You can see libc.rip. Let's try libc. That sounds good. No, go away. Oh my god. You can also use, if you there's like libc what's it called? There's a lot of code that you can use to download your own offline libc database and so forth, which if you're really passionate about this, oops, you can probably do. All right, let's put in the addresses and the symbols. Hit find. I'm going to take this to mean it didn't found it. Yeah, man, what the hell? Okay, let's actually try. Maybe it has its actual symbols. Let's try read. And puts. Remove the, oh, you can't remove the last time. Here. Aha! Okay, my bad. So I don't know, the desync there between GDB symbols and symbols here, maybe my best guess, there are multiple symbols pointing to this piece of code, and this is what GDB chose to display. But you put in the symbol, you put in the address, you hit find, and it gives you 3 potential candidates, right? How do we narrow it down? Well, we can leak more stuff and find more. I mean, in fact, we don't have to have 2, you can have 1. Just give us more potential candidates. Already, I mean, this is what, 10, 15, whatever, 11 candidates. You can just try and exploit 11 times with the different gadget addresses, right? So already, just by leaking this, the PLT, we can, or the GOT, we can find where libc is. So let's take a look at this in practice. And let's make read puts. Let's see. Okay, here's a very mean program, and we can compile it. Read puts. All it's going to do is read our input, tell us to go away. All right. So nice and simple. But of course, if you overflow the buffer, then it'll crash. And then, of course, we can start wrapping. We don't know where the stack is, doesn't matter. The stack's not executable, doesn't matter. We know where the program is. We really only have 15 minutes in the class. Fuck. We know where the program is, so we can make this work in 15 minutes, no problem. All right. Let's import pwn and what is going on with my machine? Is this really just, I need a new computer. Okay, import pwn. All right, let's launch read puts. And we're going to actually, Let's figure out where the buffer is. Okay. Look at our core. Here we go. No, come back. No. No. Okay. There we go. 136. So we're going to give it 136 bytes of padding. Okay. And the address, what do we want to do? As I said, we want to leak out the GOT. This is our first goal. We're going to leak out the GOT. How are we going to do that? Well, puts is in the binary already. We know the address of the PLT stub of puts because we know the address of the binary. There's no PIE. So we are going to let me close this side there. So we are going to jump to the PLT stub of puts 401050. And the common thing, if you have puts, is to puts the GOT address of puts, right? Because by the time puts is running, that address will be nice and updated with a libc address. All right. And that's going to be this guy. So we want to jump here and we want to what's it called? To pass that as an argument. And now, of course, we are going back to our P++. For this guy, pop RDI, the first argument. So our ROP chain is going to be pop RDI. Connor, have you had an office hours yet? You have one tomorrow, so you haven't shown them how to do find gadget. All right. So Connor will show you how to like basically do this with pwn tools. I'm not gonna do it right now, but my thing, I'm a bit of a out of touch Luddite here. I just create constants. So pop RDI ret equals this. Whoa, man, what the hell? Actually, I don't do this anymore. Now I actually do use pwn tools properly, but this is easier for the demo. All right, and Connor will show you in office hours how to do this with pwn tools tomorrow. All right, pop RDI ret. So now we need the address of what we want to print out. And that's this guy. Then we want to give the return address. So this is GOT of puts. Now this is going to be the PLT of puts. Is where we're going to jump to. Okay, and puts runs. Then when we return, we see this. And if you recognize 15A0, or really 5A0, that is the offset of puts of my libc. And that is the address of puts in my libc. So we can let's actually read the line that says no flag for you. That's not very nice. And then we read the next line, except for the last letter. And then we unpack it, and this is going to be puts adder. Okay. That's not very nice at all. Oh, okay. Now, why is this 6 bytes long? Because user space addresses begin with 0, 0, right? And in this case, actually 0, 0, 0, 0 on Linux. So we have 2 0 bytes at the most significant bytes of our puts address, which are the rightmost bytes. And of course, puts will print a string, so it'll stop reading at 0, 0. No problem. We just adjust to 8 characters with null bytes. I actually want this. Okay, perfect. So now we have the puts adder in hex. What? Oh, no. I unpacked it. No, I didn't. Okay, puts adder, put it on hex, boom, that's an address. Every time you run this, it's going to be different because of ASLR, right? But we don't care. Now we know where it is. How do we get the libc base? Get libc, grab for puts, -s, -d, just keep hitting, boom, nope, -D. Oh, got it, okay. This looks like our guy. Oh, yeah, I was right. There are 2 different symbols pointing to puts. All right, this is the offset in libc of puts, as nm is a command that lists symbols, and libc defines symbols that says, hey, puts is hex 87580 bytes into this file, which obviously is wherever it's loaded in memory plus that much. And that's actually how DL resolve, actually, which we were stepping through earlier in libld, finds it. Okay, cool. So this means we have the libc adder. Okay, as a sanity check, our libc adder is going to be page aligned because files are loaded on page aligned basis. So now we have the libc adder. Now we can find anything in libc at all. And we have 5 minutes to do it, and we will do it. All right. So what do we do now? Because the program's dead, right? Well, the program doesn't have to die. We know where the program is. We can run whatever we want. We can, for example, return to the read PLT stub after setting up RDI, RSI, and RDX properly to read in more bytes. But luckily, the program already has functionality to do that for us. It's called the main function. So we're going to return back into the main function. The main function is here. And this will be where puts returns to, because when puts is executed, of course, it expects the return address to be on the stack. And now if I run this, it's going to hang. Oh, no, it's not. But it's not dead. It is just acting very weirdly because we really screwed it up and looped main again. But the point is that here, after here, we know where libc is, but the program's still alive and reading again. And we can give it now a new drop chain. And now we know everything. Let's just call the exit syscall so that we can all go home. But now we can use libc gadgets. Actually, let's just find the syscall gadget and call it a day. You know where pop RDI is. So let's see, new plan. Okay, we're gonna send it 136, pop RDI. RDI is gonna be 42. This is gonna be a great success. This is the return code. And this is going to be libc adder plus the syscall gadget. Let's use this as, well, this syscall gadget will allow us to continue execution, but we don't really care. It's gonna exit, but it's fine. So libc syscall, libc adder plus that. Okay. libc syscall, and I have an errand plus sign, and it didn't work. Oh, of course it didn't work. Why didn't it work? Because we didn't set the syscall number. We just ran syscall, right? With RDI 42. I don't know what RDI 42 is, but for whatever reason, that hung the binary. So let's just find, again, we have any gadget we want. So if you want pop RAX, we got pop RAX. Pop RAX red, we got 19 of them. We can hand them out for Halloween. All right. Oh, yeah, okay. And you'll notice I am mixing gadgets in libc, not in libc. Who cares? It's the same memory space. It's fine. They're all executable. What is the return, the syscall number of exit? (3C). Awesome. Boom. Start with return code 42. Of course, we have all the gadgets we need. It's just as easy to build the full whatever rob chain you want, the rob chain of your dreams. But for us, we wanted to end class relatively on time. So we just demonstrated control by controllably exiting with that. Again, what did we go over today? The program linkage table, the PLT, procedure linkage table. Program or procedure? Procedure linkage table, right? Procedure linkage table. Anyways, I'm running on, as usual, like 3 hours of sleep, so it's no good. We went over the PLT. That's where you jump to that then reads the address out of the GOT of the hopefully resolved function and jumps there. If the function has been resolved yet, the address in the GOT points to the resolver stub for that function in your binary. That resolver stub pushes an identifier of that function onto the stack and calls the general resolver stub in your binary, which calls DL resolve, which resolves the symbol, jumps there. And from then on, the GOT, the DL resolver function, before jumping there, it'll update the GOT with that address, so you don't have to go through that again. Once it updates that, if you know where the GOT is, then you know what to leak out to get a libc address. All right, awesome stuff. You will need to use the skills we learned here, including jumping back into main to get another go at exploitation. Because of course, if you hadn't done that, if you had allowed this program to die, then the address we got is obsolete, because the next run, ASLR would re-randomize the address space. All right, thank you for joining us. Again, push onwards with ROP. I wouldn't count on that extension. I know we've been, I mentioned several times earlier that historically we've had to extend ROP, but people are getting through it a lot more effectively this year for whatever reason. So we'll see you Thursday, hopefully with some heat. Goodbye.